Okay, so we left off Tuesday, all right? 12:3, we were finishing up talking about the following. So we're going to go ahead. We had left off doing the experiment with the light bulb. Talked about how ionics were great conductors once they were dissolved in a liquid phase. They were not good conductors in a solid phase, right? And we talked about how that affected the human body, right? So go back and review those notes. And so I'm going to pick up now on the next slide here, and we're going to talk about covalent bonding. Remember, covalent bonding deals with molecules. Ionic bonding deals with fill in the blank. Hopefully, fingers crossed, you said compounds, right? So ionic bonding makes compounds. Covalent bonding makes molecules. That's one of the first differences you need to know. Covalent bonding occurs when you have pairs of electrons that are shared between non-metals. There's no more metal and non-metal, right? You've got two non-metals, so anion bonded with an anion, if you want to think about it that way. But they are shared. Remember, the word covalent literally translates to shared valence electrons. And they have an electronegativity difference greater than 2. Remember that ionics had the electronegativity difference less than 2. And they form polyatomic ions. Now you're going to get a whole list of polyatomic ions that you're going to go through and use. You may already have it to your advantage, but if not, I'm going to redistribute that list so that you have that as we go through. Properties. They have low melting points, and they have low BP. What do you think BP stands for? Somebody. Boiling points, right? Melting points, boiling points. It's not blood pressure. Okay, they are relatively soft solids as compared to ionics. Remember, ionics were a little harder. And they do not conduct electricity in any phase. Recall, ionics conduct electricity as a liquid, right? And metals conduct electricity as a solid and a liquid, okay? So keep all of your conductivity straight as we go through this. Covalents do not conduct electricity at all in any phase. Covalent ionic metallic bonding, right? These are some examples. We'll go through more of these in class and go through things like electronegativity. I'll give you a chart for those. You don't have to do anything with these right now. We're just going to kind of skip through the slide, but know that we will revisit this and make sense of this when we're back together. Okay? All right, let's see how many more there are here. Skip through these. All right, so the goal here is for you to be able to identify, let me go back, identify which ones are covalent, which ones are ionic, which ones are metallic, right? So what I'd like for you to do is, you should be able to do this. Let's identify the ionics out of this group, right? Ionics means they're made of a metal and a non-metal. So take a moment and jot down out of the group that's up here. You've got, what, 5, 10, 12 items up there, right? So out of those 12 items, pick the ones that you believe are ionic, or in other words, are formed between a metal and a non-metal. You can use your table to help you if you want to, but take a few minutes and do this. I'm going to have you submit it electronically, right? So you got kind of a little quiz today. What I want you to do is take the next few minutes, pause it, tell me which ones are ionic, okay, without cheating. Don't look them up. Just submit to me. I'll make a little spot in Google Drive here, in the Google Classroom, I'm sorry, where you can submit that, and that'll be a form of a quiz, okay? So pause it, give me the list of items that you see that would be ionic in nature only, okay? All right, moving forward. If we start talking about Lewis dots, that basically shows you how many valence electrons they have at their disposal as you move across the table. And group 1 has a +1 charge because they have 1 valence electron. Group 2 has a +2 because they have 2 valence electrons. We are leaving out the transition metals and skipping all the way over to boron. Boron group's a +3 because it has 3 valence electrons. You guessed it. As you go to the carbon group, you got 4, right? Then we start to make some changes. Okay, when you get to group 5, nitrogen group, right? You have 5 valence electrons, but you don't say +5 anymore, right? You don't say +5. You say it is -3 because they are missing 3 to complete their octet. So they don't have extras. They now need some to complete their octet. So once you get to 5 and above, you're going to get negative charges. So for nitrogens, it's -3. For the oxygens or chalcogen group, it's -2. They have 6, so they're missing 2. For fluorine or the halogen group, right, they have 7, so they're missing 1. So they're going to have a -1 charge. And then over your noble gases, right, over here in your noble gases, they already have 8. So they have 0 charge. They don't want to bond, they don't want to react, they don't want to do anything because they already have all 8 established in their valence shells. Okay, so let's move forward here. Good stuff, good for you to see, great for you to hear it explained. Keep that in mind. Right? A couple things here as we go through Lewis dots. The symbol represents the kernel of the atom, right? The nucleus and the inner electrons, basically. So when we say kernel, that's what we mean. We're not talking popcorn or anything. And the dots represent your valence electrons, as we just talked about. Okay? Good stuff. All right, sodium chloride says, how did we get here, right? If we look there, you've got the dots picked out. There's chlorine, right? There's sodium. Sodium, we said, was a +1, so you just see the plus. Chlorine's a -1. And so what happens is that +1 scoots over, right, and will join with the chlorine. So you get this +1. It's going to come over here and fill in, right? And now you've got 2, 4, 6, 8 around chlorine, right? And if you were to go back and look in the earlier slides, you'd see that that also leaves this with 8. But that's what happens in an ionic bond, metal plus a nonmetal, right? Let's see. I think I'm going to kind of skip through some of this a little bit. This is the steps for telling you how to do the electron dots, right? And so we're just going to kind of skip through some of this. Drawing loose diagrams. If you want to, go ahead and practice. I'm going to go back. You can practice a few of these. Take a moment, go through, see if you can draw them out. Lithium, for example, how many would it have around it? Fluorine, how many would it have around it? Follow your rules from the previous slide if we go back. The rules are here. I think they're pretty self-explanatory. I'm not going to take a ton of time to read through these. They're very self-explanatory about how to do that. If you have questions about these, jot them down and we will go over them Thursday in class. Okay? So do copy those questions down if you do find it difficult. I think it's pretty self-explanatory. We did NaCl together. These are done almost identical to that. They'll be a little different here and there, but nothing extraordinary. All right, now we're drawing molecules using Lewis dot structures. Symbol still represents the kernel, the nucleus, and the inner electrons. Right, and the dots still represent the valence electrons. Nothing really earth-shattering or different. We've already talked about this, right? Always remember that atoms are trying to complete their outer shell. That outer shell we refer to as the valence shell, right? Hopefully you remember that. The number of electrons that the atom needs is the total number of bonds they can make. Now, let's say that again. The number of electrons the atom needs is the total number of the bonds that they can make. So, if an electron needs, an atom, needed 3 electrons to complete its octet, that means it can bond up to 3 times. That's all it means, right? So if you look at the example here, hydrogen, right? Hydrogen has one electron, right? So it means it could bond one time. That's it. Oxygen, if you look at it, it has 6 electrons, which means it needs 2, so it could bond twice. And I'm going to let you look at the other ones back through here. So from fluorine, nitrogen, chlorine, and carbon, you tell me, right? How many bonds would those guys be able to make? You need to be able to do that. You're going to see that on the exam, on your final in December, right? Which is a couple weeks. A couple weeks is going to happen fast, right? And so there's your answers, okay? All right, moving forward. Methane, here's a finished Lewis dot structure. You got methane, which is carbon. If you notice, carbon had 4 dots around it, which means that it needed 4. So it could have 4 bonds that would occur. And so what you see here then is carbon by itself would have 1, 2, 3, 4 dots. It would have 4 open sites, so it would bond 4 times. And so what you see is an H, 1H, 2H, 3H, 4H, bonding to it, right, to complete the octet. So now it's got 2, 4, 6, 8. And each hydrogen now has a pair. Hydrogen can only hold 2. So H is 2, H2, 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 right? It makes complete sense. Again, if you don't get it and you're scratching your head about it, jot down the question and I'll go over it with you on Thursday to make it a little more clear. All right, let's see where we're at. Step 1, count the total number of valences that are involved. So again, for carbon, carbon had 4, right? That's step 1. Step 2, connect the central atom, usually the first in the formula, to the others with single bonds. Carbon had 4, that means it needed 4. So 4 single bonds would go around it. That's what you saw happen. Step 3, complete the valence shells of outer atoms. Remember, they're trying to get to what magical number? Hopefully you said 8. The octet, we're trying to fill the octet rule. Right? So that's where they're trying to end up at. Step 4, add any extra electrons to the central atom. And then finally, right, if the central atom has 8 electrons surrounding it, you're done. Right? That's as many as it can hold. It will not hold any more. Okay? That's what you know is you're done. So good stuff here as we go forward. Sometimes, right? Sometimes you only have 2 atoms, so there is no central atom, but follow the same rules, right? Follow the same rules. If you notice below, the chlorine, the bromine, the hydrogen, the oxygen, and the nitrogen, those are all what we would refer to as earlier in the year, earlier in the semester. Somebody starts with a D. Diatomic, because they exist in pairs, right? Diatomic, because they exist in pairs, right? And I think if you would see these put together, you'll notice that they still have a full octet in that way. So that's nice to note. We can have double bonds. We can have triple bonds, right? So you can have single, double, or triple bonds. Let's talk more about that in person. Right now, you just need to know the following, what's on the screen. There are double bonds, there are triple bonds. In a double bond, they're sharing 2 pair of electrons. In a triple bond, they're sharing 3 pair of electrons, okay? And you'll see them line up. There you go. So at the top, oxygen, you got 2. Nitrogen down there, you've got 3. Okay, good to note. Let's see. Let's skip over this for right now. If you want to try some of those, you could. Okay, definitely try them if you need to. Let's see, polyatomics. I do not want you going and drawing these with polyatomics right now. Do copy down the rules, right? But don't do anything with them yet. Okay, so that's where we're going to leave off today. Make sure you've got good notes. Go back, pause anything that you need to pause, and submit your quiz, if you will. I'll create a place for that as well. Also submit the notes from today digitally, okay? The lecture right now is only 15 minutes. You should have plenty of time, using your time wisely in class, to submit the notes digitally as well today. Get it done. I will only take them today.